Today we are going to learn about mastering indexing for query optimization. You'll discover how to use indexing to reduce query execution time and enhance database efficiency, along with skills to implement and manage indexes effectively. Welcome to our session on mastering indexing for query optimization. Indexing is a powerful tool that significantly enhances query performance by reducing execution time and improving overall database efficiency. This video will guide you through the essentials of indexing, including the different types of indexes, how to select the right columns for indexing, and strategies for maintaining index health. By the end of this video, you'll have a comprehensive understanding of how to implement and manage indexes to optimize database performance effectively. Indexing is a technique that improves the speed of data retrieval operations on a database table. Think of an index like an index in a book, which allows you to quickly locate information without having to read the entire book. In databases, indexes serve a similar purpose by allowing the database engine to find and retrieve data rows more efficiently, which can lead to dramatic performance gains. Without indexes, a database might have to perform a full table scan, reading every row to find the necessary data, which can be highly inefficient, especially with large datasets. By implementing indexes, queries can execute faster and consume fewer resources. Real-world examples of effective indexing include significantly reduced search times in e-commerce platforms and faster report generation in business intelligence applications. Indexes in databases can be broadly categorized into two types: clustered and non-clustered. A clustered index determines the physical order of data in a table. Each table can have only one clustered index because the data rows themselves can be sorted in only one order. On the other hand, a non-clustered index creates a separate structure that points to the data, allowing multiple non-clustered indexes per table. The choice between these index types depends on specific use cases. Clustered indexes are ideal for columns with high uniqueness and are often used for primary keys. Non-clustered indexes are suitable for columns that are frequently searched for specific values, such as foreign keys or columns used in where clauses. Understanding the impact of these indexes on data storage is crucial, as clustered indexes can lead to faster retrieval times at the cost of slower data modifications, while non-clustered indexes can consume additional storage space.
Selecting the right columns for indexing is a critical step in optimizing database performance. High selectivity columns, which have many unique values, are excellent candidates for indexing because they reduce the number of rows the database engine must scan. The order of columns in a composite index also matters. It's important to place the most selective column first to maximize efficiency. While indexes can significantly speed up data retrieval, over-indexing can lead to increased maintenance overhead and slower data modification operations. Therefore, it's essential to strike a balance by analyzing common query patterns and indexing columns that are frequently involved in search, filter, and join operations. By aligning your index strategy with common queries, you can ensure that the database performs optimally without unnecessary overhead.
Index fragmentation occurs when the logical order of pages in an index does not match the physical order, leading to inefficiencies in data retrieval. Fragmentation is often caused by frequent insertions, updates, and deletions, which disrupt the optimal order of index pages. This can lead to increased I/O operations and slower query performance. Detecting fragmentation involves analyzing the index structure to assess the extent of disorder. Tools and queries are available to measure fragmentation levels, and routine maintenance tasks such as reorganizing or rebuilding indexes can help reduce fragmentation and restore performance. Understanding and managing fragmentation is essential for maintaining a high-performance database environment.
Join operations are common in relational databases, where data from multiple tables is combined based on related columns. Indexes play a critical role in optimizing these operations by reducing the number of rows that need to be processed. Indexing foreign keys and columns involved in join conditions can significantly enhance performance. Composite indexes, which cover multiple columns, can be particularly effective for complex joins by providing a direct path to the required data. However, it's crucial to avoid join pitfalls such as joining on non-indexed columns, which can negate the benefits of indexing. Careful planning and analysis of join patterns can lead to optimized query performance and efficient data retrieval.
Monitoring index usage and performance is crucial for maintaining an efficient database system. Regular analysis of index activity helps identify unused or underutilized indexes, which can be candidates for removal to reduce overhead. There are various tools and techniques for monitoring, such as database management software that provides insights into index usage statistics. By analyzing the efficiency of existing indexes, database administrators can make informed decisions about adjusting their indexing strategy. Continuous monitoring and adjustment ensure that the database remains optimized as data patterns and query requirements evolve over time.
Maintaining index health is an ongoing process that involves regular maintenance tasks such as reorganizing or rebuilding indexes. Reorganizing is a lightweight operation that defragments the index pages, while rebuilding is a more intensive process that completely recreates the index structure. Scheduling these tasks during off-peak hours can minimize their impact on database performance. Balancing the need for maintenance with the desire to maintain high performance is critical, as excessive maintenance can consume resources and affect system availability. Automating index management through scripts or database management tools can streamline these tasks and ensure that indexes remain in optimal condition without manual intervention.
Creating indexes involves careful consideration to avoid common pitfalls that can negate their benefits. Over-indexing, or creating too many indexes, can lead to increased maintenance overhead and slower data modification operations. Indexing low selectivity columns, which have few unique values, often results in minimal performance gains while consuming resources. It's also important to consider the impact of indexes on data modifications, as frequent updates or deletions can lead to fragmentation and reduced performance. Neglecting regular index maintenance can cause indexes to become inefficient over time. Poor index design, such as creating unnecessary composite indexes or ignoring query patterns, can lead to suboptimal performance. By avoiding these pitfalls and applying best practices, you can create effective indexes that enhance query performance without introducing unnecessary overhead.
As database technologies evolve, so do the techniques for indexing. Advanced indexing strategies such as filtered indexes, which apply to a subset of data, can optimize queries with specific conditions. Covering indexes, which include all columns referenced in a query, can eliminate the need to access the table, further improving performance. Indexing for partial data, such as JSON or XML fields, is becoming increasingly important with the rise of non-relational databases. Understanding these advanced techniques allows for more precise and efficient index application. Staying informed about emerging indexing trends ensures that your strategies align with current best practices and technological advancements.
In this case study, we'll explore a real-world example of successful indexing implementation. The organization faced challenges with slow query performance and high resource consumption. By analyzing query patterns and identifying critical columns for indexing, they developed a comprehensive indexing strategy that included both clustered and non-clustered indexes. The results were impressive. Query execution times were reduced by over 50%, and system stability improved significantly. Key lessons learned included the importance of continuous monitoring and the need to align indexing strategies with evolving data patterns. This case study highlights the transformative impact of effective indexing on database performance and efficiency. As we conclude this session on mastering indexing for query optimization, let's recap some key concepts. Indexing is a powerful tool for enhancing query performance and overall database efficiency. Ongoing maintenance and monitoring are crucial for sustaining index health and performance. Continuous learning and adaptation are necessary as database technologies evolve. We encourage you to implement the strategies discussed today and explore additional resources for further learning. Thank you for joining us, and we hope you now feel empowered to optimize your database with effective indexing.